Starting with maths, patterns and formulas. Patterns occur everywhere in art, nature, science and especially mathematics. Being able to recognize, describe and use these patterns is an important skill that helps you to tackle a wide variety of different problems. This unit explores some of these patterns ranging from ancient number patterns to the latest mathematical research. Patterns occur everywhere in art, nature, science and especially mathematics. Being able to recognize, describe and use these patterns is an important skill that helps you to tackle a wide variety of different problems. This unit explores some of these patterns ranging from ancient number patterns to the latest mathematical research. It also looks at some useful practical applications. You will see how to describe some patterns mathematically as formulas and how these can be used to solve problems both by hand and using a computer spreadsheet. At the end of the unit, you can even have a go at an unsolved mathematical problem. Between 2000 and 2002, a $1,000,000 prize was offered for its solution. That's just to show you that there is still a lot of very exciting mathematics to be discovered, and also that everybody, you, me and all great mathematicians do get stuck with mathematics somewhere. You won't need a computer to do this though. This unit is from our archive and is an adapted extract from the Open University course starting with Maths Y162, which is no longer in presentation. If you wish to study formally with the Open University, you may wish to explore the courses we offer in the Openings program. Learning outcomes. After completing this unit, you should be able to visualize problems using pictures and diagrams, recognize patterns in a variety of different situations, use a word formula to help solve a problem. Derive simple word formulas of your own, for example for use in a spreadsheet. Use doing and undoing diagrams to change formulas around. Solve problems involving direct and inverse proportion. Interpret and use notation for inequalities. Appreciate that there are many unsolved problems in mathematics. 1. Exploring patterns and processes. Suppose you are tiling a bathroom or kitchen and the last row of square tiles is to be a frieze made up of blank tiles and patterned tiles as shown below. Figure 1. A friend has offered to help. How would you describe the pattern and how to arrange the tiles? There are lots of ways of tackling this. For example, you might say that you will need some blank tiles and some patterned tiles with the bridges on. Start with a bridge tile, then put a blank tile next to it. Take another bridge tile, but turn it round so that the bridge is upside down, like a smile, and put it next to the blank tile in the same line. Then put another blank tile next to the smile tile. This is the pattern. Just carry on. Bridge, blank, smile, blank, bridge, blank, smile. Or you may have decided to draw a picture of the tiles, or demonstrate the pattern with the tiles themselves. Whatever you do though, it's probably easier to remember and apply if you have recognized that the pattern is a 4-tile repeat with the 2 different types of tile. The frieze is an example of a type of geometrical pattern that has many applications in art, crafts and design. The next example is a number pattern which appeared in China and Persia over 700 years ago, but is still used by students in mathematical and statistical problems today, and it even appears in chemistry. It is known as Pascal's triangle, named after Blaise Pascal, who was a 17th century French mathematician who studied the properties of this triangle, and the first part of it is shown below. Figure 2. You can continue the triangle indefinitely by following the pattern. Each row of numbers starts and ends with the number 1. Look at each pair of numbers in the last line above. For each pair, add the 2 numbers together and write their sum on the line below as shown. This process generates the next row of the triangle. Figure 3. Activity 1. Pascal's triangle. Using the hexagonal paper attached in PDF format below, write down the numbers in the next 2 rows of Pascal's triangle. Hexagonal paper. Can you spot any patterns in the numbers in the triangle? What do you notice about the sum of the numbers in each row? If this pattern continues, what do you think the total for the 10th row will be? Keep this paper handy as you will need your triangle later in the unit. Discussion. The next two rows are 1, 7, 21, 35, 35, 21, 7, 1 and 1, 8, 28, 56, 70, 56, 28, 8, 1. There are many different patterns. The ones down the sides of the triangle is probably the easiest one to spot. You can also see the counting numbers 1, 2, 3, 4, 5 in the diagonal rows next to the sides. In the next diagonal row, there is the sequence 1, 3, 6, 10. These numbers are known as the triangular numbers because they create triangular patterns. Figure 4. The triangle is symmetrical too. If you draw a vertical line down through 1, 2, 6, one side of the triangle is a mirror image of the other. Figure 5. Do not worry if you did not spot all these patterns. Looking at the diagonal row of triangular numbers, if you add any two adjacent numbers together, you get the square numbers. For example, 1 plus 3 equal 4, which is the same as 22. 3 plus 6 equal 9, which is the same as 32, and so on. The pattern in the powers suggests that the first total, 1, might be written as 20. Check on your calculator to see if this is correct. Does any number to the power 0 give you 1? Now, if you add together the numbers in each horizontal row, you get the following pattern. 1, 2, 4, 8, 16, 32, 64. The total for the next row is double the total for the current row. Assuming this pattern continues, the total for row 8 will be 128, row 9 will be 256, and row 10 will be 512. You might have spotted that these numbers can also be written as 1, 21, 22, 23, 24. What have these two examples to do with mathematics? Well, recognizing patterns in shapes, sets of numbers, processes or problems generally, and spotting what is the same and what is different about situations often makes the task easier to solve. You saw how recognizing the tiling pattern makes it easier to remember, and by using the number patterns in Pascal's triangle, you could work out the sum of each row without adding up the individual numbers. If you can spot a pattern and then describe what happens in general, this can lead to a rule or formula. Provided you can prove that this rule will always work, it can then be used elsewhere. For example, if you can work out the general process for calculating a quarterly electricity bill and then give these instructions to a computer, many electricity bills can be generated, printed and sent out in just a few minutes. 2. Looking for relationships. In this section, we are going to consider the relationship between quantities in two practical situations and see how to describe these relationships by writing down a general rule or a word formula. Suppose you are planning a visit abroad. Your map marks all the distances between places in kilometers rather than miles. How can you work out what these distances are in miles? Figure 6. The first bit of information you will need is how long 1 kilometer is, if it is measured in miles. According to a dictionary, 1 kilometer is equivalent to approximately 0.6214 miles. The next step is to work out the mathematical process you will need to use to change kilometers into miles. You may be able to see how to convert from kilometers into miles immediately, but, if not, try to visualize a few simple examples first. Drawing a diagram often helps. Each km is the same as 0.6214 miles as shown below. Figure 7. So if the distance is 3 kilometers, you will have 3 lots of 0.6214 miles. If the distance is 10 kilometers, you will have 10 lots of 0.6214 miles. If the distance is 250 kilometers, you will have 250 lots of 0.6214 miles, and so on. You can write this down mathematically as 250 kilometers equal 250 0.6214 miles equal 155 miles to the nearest whole number. Notice that in each of the examples above, the process for calculating the number of miles was the same. Multiply the number of kilometers by the conversion rate of 0.6214. This technique will work for any distance and can be written down concisely as the following word formula. Distance in kilometers 0.6214 equal distance in miles. This is the same as writing distance in miles equal distance in kilometers 0.6214. You can use this formula to convert any distance in kilometers into miles. For example, suppose you wanted to convert 500 kilometers using the formula, and replacing distance in kilometers by 500 gives distance in miles equal 500 62 14 equal 310. 7. So 500 kilometers is equivalent to approximately 311 miles. In this example, you use the formula by replacing the phrase distance in kilometers in the right-hand side of the equation by the corresponding value, 500. This is known mathematically as substituting the value into the formula. Activity 2. How many miles? How far is 350 kilometers in miles? Discussion. Substituting 350 for distance in km gives distance in miles equal 350 62 14 equal 217. 49. So 350 kilometers is approximately 217 miles. Activity 3. Exchanging currencies. Suppose you wish to exchange some money in pounds sterling into euros. At the time of writing, one agency had an exchange rate of 1.48 to 1 and did not make any additional charges. If you prefer, you can look up the current conversion rate in a newspaper or at a bank or travel agency. How many euros would you get for 5? How many euros would you get for 10? Write down a word formula that you can use to convert pounds into euros. Your formula should start number of euros equal. Check that your formula works by using it to convert 5 into euros. Discussion. For each pound, you would get 1.48, as shown below figure 8. So, if you exchange 5, you would get 5 lots of 1.48. So 5 equal 5? 1.48 equal 7.40. If you exchange 10, you would get 10 lots of 1.48. So 10 equal 10? 1.48 equal 14.80. To change pounds into euros, you need to multiply the number of pounds by the exchange rate of 1.48. So the word formula is number of euros equal number of pounds 1.48. See, substituting 5 for number of pounds gives number of euros equal 5.148 equals 7.40. This agrees with the answer in part A. What would happen to the formula if there was also a handling charge? These two examples illustrate how a word formula can be used to summarize some mathematical process, such as converting units of length or currencies. Once a formula has been derived, it can then be used in other situations, both for calculations by hand or by computer, for example for currency transactions in a bank. You will be able to practice writing down some more of your own formulas in sections 4 and 5. 3. Using formulas. 3. 1. Introduction. In the last section, we considered how a formula could be built up and then how it could be used. This section considers some more complicated formulas, which have already been developed and are used in a variety of different situations: cookery, healthcare, business and archaeology. We hope that these examples illustrate some of the very broad applications of maths and how mathematical relationships can be used in making decisions. As you work through these examples, you may like to consider where else maths might be used in each of these topics. When you are trying to solve a real-life problem mathematically, you often use formulas that have already been developed, so it is important to have some ideas for how to apply these. This section will help you to do that. You may like to make your own list of tips as you work through this section and compare it with the box at the end of this section. 3. 2. Maths in cookery. The time taken to cook a fresh chicken depends on its mass, as given by the following formula. Roughly how long will a chicken with a mass of 2 kilograms take to cook? To use the formula, you need to substitute the mass of the chicken into the right-hand side of the equation and then work out the resulting calculation. However, the formula asks for the mass in grams, so the first step is to convert 2 kilograms into gram. Since there are 1,000 grams in 1 kilogram, 2 kilograms equal 1,000 grams equal 2,200 grams. Substituting 2200 for the mass in G gives. Carrying out the multiplication and division first gives. Cooking time in minutes equal 15 plus 110 equal 125, so the cooking time would be about 125 minutes or 2 hours and 5 minutes. If you prefer, you can use your calculator, but remember to make an estimate first so that you can check that your answer is reasonable. Figure 9. Activity 4. A smaller bird. How long would it take to cook a chicken with a mass of 6 kilograms? Discussion. Converting 6 kilograms into gram. 6 kilograms equal 1000 grams equals 1600 grams. So the cooking time in minutes. Minutes equal 15 plus 25 equal 95. The chicken would take about 95 minutes or 1 hour 35 minutes. 3. Maths in healthcare. The body mass index BMI is sometimes used to help determine whether an adult is under or overweight. It is calculated as follows. Although care needs to be taken in interpreting the results, for example, the formula isn't appropriate for children, old people or those with a very muscular physique. A BMI of less than 20 suggests the person is underweight and a BMI of over 25 suggests the person is overweight. In this formula, the units have been included in the expression on the right-hand side of the equals sign. It is important to change any measurements into these units before you substitute the values into the formula. No units have been included for the BMI on the left-hand side, in line with current healthcare practice. However, strictly the unit for the BMI is which is the same as or kilograms per square meter. Activity 5. Body mass index. If an adult man is 176 centimeters tall and has a mass of 85 kilograms, calculate his BMI and decide whether he is overweight. Discussion. The formula needs the mass in kilograms and the height in meters. So convert the height into meters first. Since there are 100 centimeters in a meter, 176 centimeters equal 176 100 meters equal 176 m. Substituting the height and the mass into the formula for the BMI gives. Since his body mass index is over 25, the man is probably overweight. Can you work out what weight he should be? Note that, if you study science courses, scientists include the units throughout the calculation, writing the solution like this. 3. Maths in business. One of the advantages of identifying the general features of a calculation and then describing it mathematically is that the formula can then be used in either a computer or a calculator program to work out many different calculations quickly and efficiently. Many utility suppliers, gas, water, electricity, telephone, have tariffs based on a fixed daily or monthly or quarterly charge and a further charge based on how much you have used during the billing period. For example, in 2005, a mobile phone network charged $5 per month for 30 minutes or less of phone calls. Extra calls above the 30 minutes were charged at 10p per minute. Assuming that more than 30 minutes were used per month, the formula for the total monthly cost was given by total monthly cost in equal 15 plus total number of minutes used 30 1. Activity 6. Understanding the formula. Suppose that 1 month 75 minutes of phone calls were made. Explain how you would calculate the cost for the extra minutes above the 30-minute allowance and hence how to calculate the total cost for that month. Can you explain how the formula has been derived? Discussion. As 30 minutes are included in the 15 charge, the number of minutes that are charged separately is 75. 30 equal 45. Each extra minute costs 1. So 45 extra minutes will cost 45 1 equal 50. So the total charge for that month is 15 plus 50 equal 50. The formula says that the fixed charge is 15, and then each minute in excess of the 30 minutes allowed costs 10p. Figure 10. Activity 7. Phone bills. On this phone tariff, what would the monthly bill have been if the total time for the calls were the following? A 48 minutes be 25 minutes discussion. A substituting 48 for the total number of minutes gives. Hence the bill for the month is 1680. Note how this calculation is set out with a concluding sentence that answers the question precisely. B. The formula only applies if more than 30 minutes of calls are made, so it cannot be used in this case. This is an important step in using formulas. You do need to check that they apply in your particular situation before using them. Here, the charge is 15 for up to 30 minutes of calls, so the charge for this month is 15 overall. 3. 5 Maths in archaeology. In several different parts of the world, footprints from prehistoric human civilizations have been found preserved in either sand or volcanic ash. From these tracks it is possible to measure the foot length and the length of the stride. These measurements can be used to estimate both the height of the person who made the footprint and also whether the person was walking or running by using the following 3 formulas. Note that no units have been included in these formulas, so it is important to make sure that the same units, for example centimeters, are used throughout the calculation. If the value of the relative stride length is less than 2, the person was probably walking, and if the value is greater than 2, 9, the person was probably running. Activity 8. Footprints in the sand. From one set of footprints the length of the foot is measured as 21.8 centimeters and the stride length as 104.6 centimeters. What does the data suggest about the height and the motion of the person who made these footprints? Discussion. The height of the person is estimated to be 721.8 centimeters or approximately 153 centimeters. To work out the relative stride length, we need to calculate the hip height and then substitute it into the relative stride length formula. The hip height is 421.8 centimeters or 87.2 centimeters, so the relative stride length 121d. P. As the relative stride length is less than 2, the person was probably walking. Notice that the relative stride length has no units. The stride length and the hip height are both measured in cm, and when we divide one by the other, these units cancel each other out, just like canceling numbers. If you go on to study physics or other sciences, you will find lots of examples like this. How do you think these formulas have been derived? How reliable do you think these estimates are? Notice that to find the relative stride length here, we tackled the problem by using the 2 formulas step by step, but you could also have combined these 2 formulas into one, and used this new formula directly. Activity 9. What's wrong? A student choose the formula relative stride length equal. To calculate the relative stride length for the person in Activity 8, use this formula to work out the relative stride length and check that your answer agrees with the result in the last activity. The student answered the key sequence for the calculation as 104.641.8. This gave an answer of approximately 570, so the student concluded that the person was probably running very fast indeed. Can you explain where the student made his mistake? Discussion. The calculator will perform this calculation from left to right, using the BIDMAS brackets, indices, division, multiplication, addition and subtraction rules, which treat multiplication and division as equally important. So it will first divide 104.6 by 4 to get 26.15 and then multiply by 21.8 to get approximately 570. However, this is not the correct calculation from the formula. The stride length 104.6 should be divided by 4 foot length, so the calculation should be 104.6 for 21.8 or alternatively 104.6 for 21.8. Enter both these expressions into your calculator directly, and check that these both do give the correct answer. Can you explain why these two calculations are equivalent? Note that the student should have been expecting an answer between about 0 and 5, so an answer of 570 is suspicious. Also, if the student had worked out an estimate for the answer first, the mistake might have been spotted. If you round all the values to one significant figure, an estimate for the answer is which is just over 1. Now, have a look back over the formulas you have used so far and also any others that you might be familiar with from your home, work or hobbies. What are the common steps in using a formula? If you were asked to jot down a list of tips for using a formula for a friend, what would you say? Here are a few suggestions. Feel free to add your own to the unit forum. Tips for using a formula. First, check the formula can be applied to your particular problem. Check what values you need to substitute and also what units these should be measured in. Convert the measurements if necessary. Substitute the values into the formula carefully. Make a rough estimate for the answer. Use BIDMAS to work out the resulting calculation, step by step. Explain your steps carefully using words like substituting and converting. Check that your answer seems reasonable, both practically and from the estimate. Round your answer appropriately. Remember your concluding sentence and the units. For your formulas using a spreadsheet. Although there may be many occasions when you are given a formula to use, sometimes you may need to devise your own formulas, for example if you use a spreadsheet on a computer at home or at work. This section looks at the process of devising a formula in more detail. Part of a spreadsheet that has been constructed to record monthly income and expenditure is shown below. It is similar to a balance sheet that you might draw up by hand and includes the monthly income and outgoings, the totals and the overall balance. It is used to keep track of expenditure, particularly to try and ensure that the balance remains positive. However, the spreadsheet has been stored on a computer rather than on paper and is updated regularly. One of the advantages of using a computer spreadsheet is that you can insert formulas into the spreadsheet to carry out the necessary calculations automatically, without using your calculator. A spreadsheet is made up of rows and columns of cells. The columns are identified by letters and the rows by numbers. This enables you to identify each cell in the spreadsheet. For example, the number 156 is in column B, row 11, so this cell is B11. Figure 11 cells can be found from their reference, by looking down the column and across the row. So cell A3 can be found by looking down column A and across row 3. This cell contains the word salary. Notice that cells can contain either text or numbers. Activity 10, Spreadsheet cells. What is contained in the following cells? A 5? A 12? B15? B1. What is the reference for the cells that contain the following? The number 792. 59. The word food. Discussion. The cell that is in both column A and row 5 contains the words total income. Looking down column A and across row 12, cell A12 contains the word other. The cell that is in column B, row 15 contains the number 83. 36. The cell that is in column B, row 1 contains the heading amount. This indicates that the entries in this column are amounts of money and that they are measured in. This heading could also have been written as amount in or amount. 792. 59 is in column B and row 13, so its reference is B13. Food is in column A and row 9, so its reference is a 9. Now have another look at the spreadsheet and see if you can work out what information it shows. For example, if you look at row 3, this shows that the monthly salary is 850. 28. Although cell B3 only contains the number 850. 28, you know that this is measured in pounds from the heading in cell B1. Overall, the spreadsheet shows the different items that make up the monthly income and where money has been spent over the month as well. If you were keeping these records by hand, you would then need to calculate the total income, the total outgoings and the balance. For example, to find the total income for the month, you would need to add the salary 850. 28 to the other income 25. 67. This gives the total income of 875. 95. In other words, to calculate the value in cell B5, you need to add the values in cells B3 and B4 together. This can be written as the following formula. Value in B5 equals value in B3 plus value in B4. Activity 11, Finding the balance. Formulas have also been used to calculate the total monthly outgoings in the balance. If you were working these calculations out by hand, what would you do? Check by comparing your answers with the values in cell B13 and B15. Try to write down the formulas for these cells in the form value in B13 equal. Discussion. To calculate the total monthly outgoings, you need to add up the individual outgoings on rent, food, transport, regular bills and other. So the formula will be value in B13 equal value in B8 plus value in B9 plus value in B10 plus value in B11 plus value in B12. To find the balance, you need to take the outgoings away from the total income. So the formula will be value in B15 equal value in B5, value in B13. To put these formulas in the spreadsheet, you can type the formula directly into the relevant cell, starting with an equal sign to show that you are entering a formula rather than a word. Figure 12. Notice that in cell B13, a shorthand form for the sum has been entered. You could have typed H equal B8 plus B9 plus B10 plus B11 plus B12, but it is also acceptable to use the shorthand form, equal SUM B8. B12, which is shown here. This instruction tells the computer to add together the values in all the cells from B8 to B12. One of the advantages of using a spreadsheet is that if you change some of the numbers, all the calculations that use that particular number will be automatically updated to reflect the change. For example, in this budget the amounts for the salary, rent and the regular bills are likely to remain the same from one month to the next and may only be updated once or twice a year. However, the amounts for food, transport, other bills and other income probably will change from month to month. These values can be changed easily on the spreadsheet and a revised balance produced immediately. Activity 12. Spreadsheet formulas. The formulas used in a spreadsheet are shown in the diagram below. Note that is the notation for multiplication and is the notation for division. Figure 13. The values in column C and D are displayed to two decimal places as they represent an amount of money. What values will be displayed in cell C3 and cell D3? B. What do you think is being calculated in the cells in column C? Can you suggest a suitable heading for this column to be entered into C1? C cell D5 should contain the total of the values in D2, D3 and D4. Write down a formula that could be entered in cell D5. What does this value represent? Discussion. The formula in C3 is value in C3 equal value in B3 0. 175. So the value in C3 equals 16. 49 0. 175 equal to 885.75. Although the full value is kept in the cell, it will only be displayed to 2D. P. S2. 89. The value in D3 is obtained by adding together the values in B3 and C3. So, value in D3 equal value in B3 plus value in C3 equals 16. 49 plus 2. 885.75, which is 19. 375.75. This will be displayed to 2D. P. as 19. 38. B. The numbers in column C are 0. 175 or 17. 5. Of the values in column B, you may know that 17. 5. is the main UK VAT rate, so it looks as if column C represents the amount of VAT paid on the different items described in column A. A suitable heading might be VAT, or VATN or VAT. See, the total can be found by adding together the values in cells D2, D3 and D4. So the formula equal D2 plus D3 plus D4 could be entered into cell D5. Alternatively, you could use equal sum D2, D4. This represents the total cost including VAT of the radio, kettle and fan. With these changes, the spreadsheet will look like the following. Figure 14. 5. Your own formulas. 5. 1 number tricks. In the last section, you worked out some formulas that could be used in a spreadsheet. Section 5 gives you some more practice in deriving formulas both by looking at some number tricks and rearranging some existing formulas. Activity 13. Think of a number. Try this number puzzle. If you use your calculator, remember to press the equal sign after each instruction. Think of a number. Add 5. Double it. Subtract 8. Divide by 2. Take away the number you first thought of. Add 4. Now if 1 represents the letter A, 2 represents the letter B, 3 represents the letter C, and so on. Work out the letter represented by your answer and write down the name of an animal beginning with this letter. Discussion. If the number 3 were chosen initially, the instructions work out as follows. Add 5. 3 plus 5 equal 8. Double it. 8 2 equals 16. Subtract 8. 16 8 equal 8. Divide by 2. 8 2 equal 4. Take away number 4. 3 equal 1. Add 4. 1 plus 4 equal 5. You will find that you always get 5, whatever number you start with. This gives the letter E. Did you choose an elephant? To see how this trick works, read through the instructions below. Because we do not know what number you have thought of, we have replaced the number by a thought bubble like this. Figure 15 that shows that the numerical answer is always 5. It does not depend on which number was chosen first of all. So the letter of the alphabet chosen is E. There are not many animals with names beginning with E, and most people do think of an elephant first, but you might be unlucky if someone chooses an emu or an eel. Rather than using a cloud to represent the number and explaining the trick pictorially, you could write down expressions for the answer at each stage and use either a word, for example, number, or a letter, for example, N, to represent the number. The trick can then be written as follows. Instruction expression. Think of a number n, add 5, n plus 5, double it, n plus 5 plus n plus 5 equal 2n plus 10, subtract 8, 2n plus 10, 8 equal 2n plus 2, divide by 2, 2n 2 plus 2, 2 equal n plus 1. Take away the number you first thought of, n plus 1. N equal 1, add 4, 1 plus 4 equal 5. Activity 15. Another number trick. Try the following trick several times. Think of a number between 1 and 10. This will work with numbers greater than 10, but the restriction is to keep the arithmetic manageable. Multiply by 4. Add 6. Divide by 2. Subtract 3. Divide by 2, and your answer is? Write down the number you first thought of and your answer. What do you notice? Can you explain why this happens, either by using a diagram or by writing down the expressions for the answer at each stage? Discussion. You should find that this time the answer is always the number you chose at the start. The expressions for the answer at each stage are shown below. Instruction expression. Think of a number between 1 and 10 and multiply by 4, 4n, add 6, 4n plus 6, divide by 2, 4n 2 plus 6, 2 equal 2n plus 3, subtract 3, 2n plus 3, 3 equal 2n, divide by 2, 2n 2 equal n. Try making up your own number tricks. What makes a good trick? 5. 2 doing and undoing. Now try the following. Think of a number. Add 4. If my answer is 11, can you work out what number I was thinking of? You might have said, what number do I have to add on to 4 to get 11? Or perhaps, if I take away 4 from 11, what number do I get? In both cases you should have arrived at the answer 7. In the second method, subtracting 4 undoes the adding 4 in the original instructions. This process can be illustrated by a doing-undoing diagram. Figure 16. In the doing part of the diagram, start with the number and write down the operations applied in turn until you get the answer. Here there is just one operation, add 4. Figure 17. For the undoing part of the diagram, start on the right with the answer, in this case 11. Then work back towards the left, undoing each operation in turn until you find the starting number. In this case, subtract 4 undoes add 4, and 11 minus 4 equals 7. So, the number first thought of was 7. Notice how the arrows indicate the direction to read the diagram. The next activity gives you some practice with doing and undoing. You will find these techniques helpful for rearranging formulas. Part D involves 2 stages. Activity 16, doing and undoing. Try to work out what number I was thinking of in the following problems. You may find it helpful to use some doing-undoing diagrams. Think of a number, subtract 3 and the answer is 2. Think of a number, multiply by 5 and the answer is 35. Think of a positive number, square it and the answer is 81. Think of a number, add 4, double it and the answer is 14. Discussion? Figure 18. So the number I thought of was 5. Remember you can check your answer by using it in the trick. 5, 3 equal 2. Figure 19. So the number I thought of was 7. Check. 7 5 equal 35. Figure 20. So the number I thought of was 9. Check. 92 equal 81. Figure 21. So, working from the right, 14 2 equals 7 and 7? 4 equal 3. If you like, you can write the output from each box on the arrow as shown above. Hence, the number I thought of was 3. Check. 3 plus 4 equals 7. 7 2 equal 14. When you have to deal with more than one operation, just take each step in turn. Write down the doing diagram and draw the undoing one underneath, working backwards to undo each operation. To summarize, the following operations undo each other: addition and subtraction, multiplication and division, squaring and taking the positive square root. Activity 17, a multi-step problem. Think of a number. Add 5. Multiply by 3. Subtract 4. If the answer is 17, can you work out what number I was thinking of? Here there are several steps, so to find the number it will be necessary to undo each of these steps in turn, starting with the last step. Draw the doing diagram and then the undoing one beneath it. Discussion. The diagram below shows the steps taken in this case and then how to undo each one. Figure 22. So if the answer is 17, undoing the steps by working from right to left gives. Add 4. 17 plus 4 equal 21. Divide by 3. 21 3 equals 7. Subtract 5. 7. 5 equal 2. So the number I thought of was 2. Check. 2 plus 5 equals 7. 7 3 equal 21. 21. 4 equals 17. The same sort of technique can be used to change formulas around. For example, earlier in the unit, you found a formula to convert pounds into euros. Number of euros equal number of pounds 1. 48. However, what if you wish to convert euros into pounds, say while you were shopping on holiday? Then you would need the formula for the number of pounds based on the number of euros. We can tackle this by drawing the doing and undoing diagrams for this situation. Figure 23. So, starting at the right of the undoing diagram, the formula for converting euros into pounds is number of pounds equal number of euros 1. 48. Activity 18. Miles and kilometers. To change kilometers into miles, you use the formula distance in miles equal distance in kilometers 0.6214. Starting with distance in kilometers, draw a doing diagram to get the distance in miles. Draw the undoing diagram and hence write down the formula for changing miles into kilometers. Your formula should start distance in kilometers equal. Discussion. The doing and undoing diagrams are shown below. Figure 24. So the formula for converting miles into kilometers is distance in kilometers equal distance in miles 0.6214. Activity 19. How many minutes for chatting? Recall the formula for the monthly cost of a mobile phone that we used earlier. Monthly cost equal 15 plus total number of minutes. 30. 1. The owner wishes to stick to a monthly budget of 5. Starting with the total number of minutes, draw a doing diagram to show the operations to find the monthly cost. Put the monthly cost equal to 5 and then draw an undoing diagram to work out how many minutes of phone calls can be made if the monthly cost is 5. Discussion. Here is the doing diagram. Figure 25. Undoing each step in turn gives the following undoing diagram. Figure 26. So applying these operations in turn. Subtract 15 gives 25. 15 equal 10. Divide by 0. 1 gives 10 0. 1 equal 100. Add 30 gives 100 plus 30 equal 130. Hence, 130 minutes can be used for a monthly budget of 25. With practice, this process of using a doing-undoing diagram does become second nature. In some cases, it can be useful if you need a formula in a different form. However, for complicated formulas, a different approach which you will meet if you continue your mathematical studies is often used. Sixth proportion. 6. 1. Direct proportion. The first type of proportion relationship is known as direct proportion. Two quantities are said to be directly proportional to each other if when one doubles, triples, quadruples, the other also doubles, triples, quadruples. For example, if you buy 3 times as many items as usual, you would expect to have to pay 3 times as much money unless there was some special offer available, because the price is directly proportional to the number of items bought. Activity 20. Directly proportional relationships. Which of the following quantities are in direct proportion? The number of kilometers and the equivalent number of miles in Activity 18. B. The number of euros that are exchanged for pounds in Activity 3. C. The monthly cost of a mobile phone and the minutes used for talking in Activities 6 and 7. Discussion. Parts A and B are both examples of direct proportion. If you multiply the number of kilometers by any factor, the number of miles will also change by this factor. For example, if you double the number of kilometers, the number of equivalent miles will also double, and similarly for exchanging currency. If you triple the number of pounds you exchange, you would expect to get 3 times as many euros. However, part C is not a directly proportional relationship. If you use 30 minutes, the charge is 15. But if you double the time used to 60 minutes, the charge is 18, and the price has not doubled. You can tackle problems involving direct proportion in many different ways. Using a formula is not always the easiest way, as the following example shows. Suppose that in a tea club at work, a group of people share a carton of milk each day, but provide their own tea. The carton contains enough milk for 12 cups of tea. If the carton costs 36p, how much should someone who has 4 cups of tea with milk pay? This person had of the milk, so should pay of the cost of the milk, which is 12p. Alternatively, you can work out the cost of milk for 1 cup of tea as a first step. Since there is enough milk for 12 cups, 1 cup will cost 36p, 12 equal 3p. So 4 cups will cost 3p or 12p. Note how the problem has been simplified by considering just 1 cup of tea first. Activity 21. The more the merrier. A recipe for a vegetable curry for 4 people requires 300 g of rice. By first working out how much rice one person requires, calculate how much rice would be needed for 9 people. Discussion. Work out the amount of rice for 1 person. 300 grams 4 equals 75 grams. Figure 27. So 9 people will need 975 grams equals 675 grams. You can work this out in other ways too. Activity 22. How much medicine? A patient needs to have 600 milligrams of a drug each day, given in 3 doses. Each tablet contains 100 milligrams of the drug. How many tablets are needed for each dose? Discussion. 1 tablet contains 100 milligrams of the drug, so 6 tablets will contain 600 milligrams of the drug. The patient will need to take 6 tablets spread over 3 doses. So the number of tablets in each dose will be 6, 3 equal 2. Figure 28. You can also use a formula here. Use the formula to see if you get the same answer. Remember to check that your answer seems reasonable. 6. To inverse proportion. The second type of proportional relationship is known as inverse proportion. Suppose you have decided to hire a taxi to take a group of colleagues from work to the railway station. If the taxi firm charges a set fee for the journey, then the more people who go in the taxi, the less each person has to pay. If 2 people go, each pays half the cost. If 3 people go, each pays a third of the cost, and if 4 people go, each person pays a quarter of the cost. This is an example of inverse proportion. As one quantity the number of people doubles or triples, the other quantity the cost halves or is reduced to a third of the original value. In other words, if you multiply one quantity by a factor, the other quantity is divided by that factor. The cost per person can be calculated directly or by using the formula cost per person n equal taxi fare in number of people. For example, if the fare is 7.80 and 4 people go in the taxi, each person will have to pay 7.84 equal 1.95. Two quantities are said to be inversely proportional if their product is a constant. For example, suppose you go on a journey of 30 kilometers and it takes you an hour to get there. Your average speed for the journey is 30 kilometers per hour. Now if you doubled your speed to 60 kilometers per hour, it would take you half as long, that is, half an hour to get there. If you have your speed, it would take twice as long, and so on. In each case, the following relationship holds. Speed in km per hour, time for journey in hours equal distance traveled in km. This shows that for a given distance, speed and time are inversely proportional to each other. This formula can also be written as Activity 23. How fast? For the journey of 30 kilometers above, what is the average speed if the journey took 1 hour? Discussion. Substituting the distance as 30 and the time as the decimal 1.5 in the formula above gives. So the average speed is 20 kilometers per hour. 7 inequalities. In this unit, there have been 3 occasions when checks have been made to see whether the result is greater than or less than some other value. The first case was in calculating the BMI and determining whether the person was overweight or underweight. The second case was in determining whether a person was walking or running from his footprints. And the third case was in checking whether a phone had been used for more than 30 minutes. Checking whether values are greater than or less than some limit happens frequently in everyday problems, particularly in safety limits, but elsewhere too. For example, medicines may have to be stored at a temperature of 25 C or less. Child rail tickets can be bought for children who are 5 or more years old but less than 16 years old. Rather than writing out greater than or less than, some shorthand notation is often used as shown below. Inequalities. Greater than or equal to. Less than or equal to. If you have difficulty interpreting these symbols, you can think of them as arrows which point to the smaller number. The symbols can be read from left to right. For example, 11. 9 is read as 11 is greater than 9 and holiday cost in 1000 is read as holiday cost is less than 000. To use the symbols in your own writing, decide what you want to say first, then use the symbol. For example, since 10 is greater than 5, this could be written as 10. 5 or cents on the number line. 4 lies to the left of 3. 4 is less than 3 and this could be written as 4. 3. Similarly, the instructions for the medicine could be written as medicine temperature in C25. Sometimes, you may find it helpful to draw a number line to visualize this sort of information. For example, the ages which children can claim the child rail fare are from their 5th birthday up to but not including their 16th birthday. This means that their age has to be greater than or equal to 5 and less than 16. Figure 29. Note how drawing a diagram here helps you to see what is happening. The empty circle means that this number 16 is not included and the filled-in circle means that this number 5 is included in the interval. This can be written as 5. Age for child rail fare. 16. Activity 24. Inequalities. Which symbol or should appear in each of the boxes below? 4. 7. 18. 10. 3. 2. Explain what the following mathematical statements mean. Balance in account. 0. Speed in mph on motorway. 70. 18. Age in years. 50. Express the following conditions using the inequality symbols. The fridge temperature should be less than 4 C. There must be at least 5 people on the committee. For an ideal weight, a person's BMI should be greater than 20 and less than 25. Discussion. 4. 7. 18. 10. 3. 2. The balance in the account is greater than 0, or in credit. The speed on the motorway is less than or equal to 70 mph. The age is between 18 and 50 years inclusive. Fridge temperature in C. 4. Number of people on committee? 5. 20. Me. 25. Inequalities are also used a lot in computer programs to check whether conditions have been fulfilled. For example, if the balance in your bank account is negative, you may be prevented from withdrawing money from a cash machine. 8. An unsolved problem. A lot of the mathematics you have looked at so far in the unit has been used to help people solve problems for centuries. However, there is much more to mathematics than that. Exciting and new developments are being made all the time, and there are many problems that mathematicians have not managed to work out. This section takes a brief look at one of these problems. It was unsolved at the time of writing. In 1742, a Prussian mathematician, Christian Goldbach, made the following conjecture. All positive even integers bigger than or equal to 4 can be expressed as a sum of two primes. A conjecture is a suggestion that has not yet been proved to be true. This statement contains quite a lot of mathematical terminology, so before going further, here are some definitions. An integer is a whole number, negative, 0 or positive. For example, 6, 23, 0 and 281 are all integers. An even integer is one that can be divided exactly by 2. For example, 8, 0, 42, 128 or 1002. The last digit of an even integer is always 0, 2, 4, 6 or 8. Integers that are not even are odd. A prime number is one that can only be divided exactly by 1 and itself. The first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59. Now, break down Goldbach's conjecture into steps. A lot of encryption processes depend on prime numbers. All positive even integers bigger than or equal to 4 means the numbers 4, 6, 8, 10, 12, and so on. Can be expressed as a sum of two primes means that you can choose any of the numbers from the prime number list to add together. For example, 8 equal 5 plus 3. Activity 25. Prime numbers. Try to express the following numbers as a sum of two primes. 62, 40, 28, 12, 4. For each number, try to find as many combinations of two primes as you can. Do you think Goldbach's conjecture is true? Discussion. It can help if you look at the list of prime numbers systematically, starting with 2. Is there a number in the list that you can add on to 2 to get the number you want? Then look at 3, and so on. You should be able to find the following combinations. 4 equal 2 plus 2, 12 equal 5 plus 7, 28 equal 5 plus 23 or 28 equal 11 plus 17, 40 equal 3 plus 37 or 40 equal 11 plus 29 or 40 equal 17 plus 23, 62 equal 3 plus 59 or 62 equal 19 plus 43 or 62 equal 31 plus 31. Are you convinced that Goldbach's conjecture is always true? Although the conjecture does work for the few numbers we have tried here, that does not necessarily mean that it is going to work for all the even integers greater than or equal to 4. The even integers go on forever, so it is not possible to check them all individually either by hand or computer. Some other way of proving the result is needed. Although higher branches of mathematics have been successful in tackling a lot of similar problems, this one is turning out to be particularly tough. So tough in fact that, in March 2000, the publishers Faber & Faber offered $1,000,000 prize to anyone who managed to prove the conjecture by March 2002, and no one did. So even though many great mathematicians have attempted a proof, over 250 years later, it still hasn't been sorted out. You might find that quite reassuring the next time you get stuck on a mathematics problem. Being stuck really is a natural state for a mathematician. It's often a time when great discoveries are made or when the best learning takes place. There is also a $1,000,000 prize on offer for each of the 7 great unsolved problems of mathematics known as the Millennium Problems. 9 patterns in nature and elsewhere. If you take a cauliflower and break off one of the florets, the floret appears to be just the same shape as the original cauliflower but on a much smaller scale. Figure 30 Romanesque cauliflower. This idea of self-similarity occurs throughout nature. The frond of a fern looks like the whole fern, a branch of a tree splits into further branches which look like trees themselves, and so on. Self-similarity now forms part of an area of mathematical research known as fractal geometry. Beautiful patterns can be generated by fractal formulas, such as the Bardsley fern and the fractal below. Fractal geometry also has many practical applications in the physical sciences, medical research, economics and computing, particularly in compressing images. Figure 31. You can generate part of a fractal yourself by using Pascal's triangle that you constructed earlier in the unit. If you shade in or cover all the odd numbers in the triangle, a pattern starts to emerge as shown below. Figure 32. This is part of a fractal known as Sierpinski's triangle. Wacław Sierpiński (1882–1969) was a Polish mathematician. It can also be generated by starting with the triangle, splitting it into 4 smaller triangles and removing the middle one. Then split each of the remaining triangles into 4 smaller triangles and remove the middle one. Carrying on in this way results in something like the sequence below. Figure 33 constructing Sierpinski's triangle. 10 Summing up. In this unit, you have looked at a variety of problems, all of which involve using patterns or formulas, and you have also extended some of your strategies for solving problems. One of the first steps in tackling any problem is to check that you understand both the problem and the information you have been given. This step can concentrate on what the question means. However, this can also involve looking up or checking on mathematical terms, notation or definitions as in Goldbach's conjecture. You may be able to sort this out yourself by referring back to your notes or books, or, if it is an unfamiliar situation, it may be easier to discuss it with someone else. Understanding the notation is also important. The notation used for inequalities is often used to express ideas concisely, and you may find it helpful to add this to your dictionary or to your notes for future use. You have already seen how diagrams can be helpful, and that applies to this unit as well. For example, a number line when dealing with inequalities. Visualizing a problem in a practical way, as in the currency exchange, can help you to work out what to do next as well. You may also like to try working through a problem with a few simple numbers first to get a feel of what's involved. This strategy was used in Goldbach's conjecture. However, although we broke Goldbach's conjecture down into steps and found that the conjecture was true for all the examples we tried, this does not prove that the conjecture is always true. A pattern isn't proof. Using formulas is an important skill, but it is important to check that the formula is appropriate for your particular problem. See the mobile phone problem, and also that any measurements are in the same units as those specified in the formula. It is easy to make mistakes in this way, so checking that the answer you obtain seems reasonable is very important too. You may like to make an estimate first as well. It is also important to check formulas you have derived yourself, particularly if you are using a spreadsheet. If you work out the numerical answer to the calculation first, you can then check that you get the same result when you use the formula in the spreadsheet. Although this doesn't guarantee that you have got the right formula, you may make the same mistake twice after all. It can help to eliminate careless mistakes. Next steps. After completing this unit, you may wish to study another Open Learn Study unit or find out more about this topic. Here are some suggestions. Diagrams, charts and graphs M124 M5 exploring data. Graphs and numerical summaries M248-1. Mathematics and statistics. If you wish to study formally at the Open University, you may wish to explore the courses we offer in this curriculum area. Starting with Maths Y182, Mathematics Education. Or find out about studying and developing your skills with the Open University. Study Explained. Skills for Study. Or you might like to post a message to the unit forum to share your thoughts about the unit or talk to other open learners. Review or add to your learning journal. Rate this unit.